Okay, in this presentation, what we have to do is find all of the spanning trees of the graph G. So this is the graph G here. There's 4 nodes, 1, 2, 3, and 4. And essentially what we have here is a series of edges there. Okay, I didn't really color that one in. Okay, now, so the first thing I can do to look at all of these nodes is actually just to sort of let's look at the degree sequence here. And it's very important for sort of informing us about isomorphism in case you are familiar with that. So just let's write in the degree sequence there. So that has degree 2, that has degree 2, sorry, 3, that has degree 2, and that has degree 3. Okay? And as you can see there that there are also 5 edges. So the total sum of the degree sequence is twice the number of edges, which is what we expect. Okay, so what I'm going to do actually in the first instance is I'm going to look at the perimeter, okay? First off, just to sort of break up the problem into digestible chunks, okay? And a spanning tree is essentially a minimal set of nodes, edges that connects all of the nodes or all of the vertices. Okay, so let's look at one here. So I have a couple ready. So essentially, in the first case, what I want is to connect all of the vertices with edges. So 1, 2, and 3. Now, that is 3 edges there, and we have all of our vertices connected. Just as a remark, I'm going to write in the degree sequence here. So this is 1, 2, 2, 1. Okay. And in the second case, what I'm going to do is just something very similar. I won't write in the degree sequence here, but I'll just actually just do it a different way. Okay. So it's essentially put in connect it using a different set of nodes in a different way, but the degree sequence will be the same. Likewise, what we could do here is this or this. Okay, so that's 4 to start off with, and in each case what we have is a degree sequence of 1, 2, 2, 1. Okay, or even better, 2, 2, 1, 1. Okay, just sort of if you reading it in a sequential order from some start to some finish, or unordered 2, 2, 1, 1. Now, what we could also do is actually try a different approach here. Okay, so what we're going to do here is actually see if we can come up with a spanning tree with a different degree sequence. So what we could do here is this: 1. Okay, so that has 1, 3, 1, and 1. That's the degree sequence there. Okay, and what we could do also is something similar here, here, and here. And again, 1, 1, 1, 3. Okay, so moving on. That's both possible cases there, because essentially at the start there are no more nodes where we have a degree of 3. So we've used them all up there. So that's as many as we can get with many spanning trees as we can get with this degree sequence here. But we're not finished yet. So 3, 1, 1. Just took a pause there for a second. Earlier on, we looked at the perimeter there, okay, to sort of see what we could work with. So in this case, what I'm going to do is I'm going to use this one here, okay, instead. Now, we actually have used some of these in this example here. So I've used this middle vertex here already in 2 cases. Okay, for the set where we had 3, 1, 1, 1 as our degree sequence. Okay, but it is possible to actually use these where we would have 2, 2, 1, 1. Okay, we've already exhausted the possibilities there of using that middle edge for 3, 1, 1, 1. Okay, we can't find any more. But essentially what we're going to do here is see if we can find 2 more using this middle edge. Okay, so it's straightforward enough. There and there. Okay, so that has degree sequence 2, 2, 1, 1. That's 1, 2, 2, 1. And what about here? So actually the last one is actually, I don't know why I did it in that order, but essentially just the mirror image of the one below. So it's no real matter if we do it in reverse order. Okay, so that's them all. So there can't be any more, and the reason is because we've used up all our nodes